So nice to see you back. After yesterday's discussion session in the evening, so I hope we could clarify a few of the questions that we had on the tutorials. Otherwise, I'm happy to continue discussions. So today I would like to continue with the other key issues that we have to understand when we want to put QCD to work. This is factorization and evolution. So yesterday we've been computing a cross-section for E plus E minus collisions, like the total cross-section, and we found that simply by applying perturbative QCD, we could get a finite number, which if you then, for instance, look at a particle data group booklet, you see that it matches experimental measurements. Yeah. Now, this applies only to a small class of observables, because for larger class of hard scattering reactions, in particular when we have initial state hadrons, we apply QCD perturbation theory, but the cross sections are not infrared safe, and that has to do with the fact that when we have initial state hadrons scattering, then they do depend on the quark and gluon degrees of freedom in the initial state, and therefore they are sensitive to the non-perturbative processes at long distances that have to do with the incoming, with incident particles. And the way out, or the concept to treat these cases systematically, is to apply factorization of the cross-section into two parts. One part, which we call the perturbatively calculable hard part, that is then supposed to be, or we can achieve to make it infrared safe after performing the factorization. And the other part is then a non-perturbative function, call it here little f. And this non-perturbative function that contains all the rest, the long distance physics, and typically we have to determine it from data. And the small f then parameterizes the hadron structure, so any long distance physics of quarks and gluons which are confined in the incoming hadrons. So that's the idea, and this is what I would like to walk you through in a couple of examples today. And so the basic relation that we want to discuss is that we have a physics cross-section. It depends on some large momentum scale, so if you think of LHC processes, it's basically the center of mass energy, or if you have the dijet event, it's the PT of the jets, something like this. Yeah? And this is of course something that experimentalists can measure, and in theory we want to describe it, and we can describe it by computing this object as a convolution of two parts, and this convolution, this happens in suitable kinematical variables. I can detail this to you later, but think of it just as a convolutional product. In terms of hard scattering cross-section, I denote this by sigma hat, meaning this is where we work with partonic degrees of freedom, and this depends on a hard scale, and then this is convoluted into some function f, which parameterizes the hadronic part of the cross-section. And you can think of this factorization as a generalization of this operator product expansion, if you're familiar with this. Right, so this is basically what I would like to discuss with you in a nutshell today. And to be more specific, if we apply this QCD factorization process, if we want to implement this for the LHC, then we get a picture like this. We have our two incoming protons, so one proton coming from the left, one proton coming from the right. And then we pull out a parton I out of each proton, so parton I here and parton J there. And then these two partons, this can be the quarks and the gluons, they undergo the hard scattering, which happens here in this gray box, and then we produce final state of interest, whatever we are interested in, like X could be Higgs boson or whatever. Yeah. So this is the part that we can do with perturbation theory, and this is described by this partonic cross section sigma head, where we have partons I and J colliding and producing a final state X. And this depends in perturbation theory. This can be calculated in powers of decoupling, strong coupling. It depends on a hard scale. We have to do renormalization. It may depend on masses. So this is this part here. And the other part is the parton dynamics inside the proton. So we have one proton on the left here, and the parton dynamics inside this proton is captured in this parton distribution function Fi here on the left, and the other one in the parton distribution function Fj on the right. And those have to be convoluted as well, and they are finally convoluted with the hard partonic scattering cross section. Yeah? And this sketchy picture here, this separates physics happening at different length scales, because the hard scattering cross section, this is happening at short distance scales, and parton dynamics inside the proton, which has a radius of a femtometer or so, this is happening at long distance scales. Yeah? And in momentum space, in order to separate these two regimes where different physics processes are happening, I've denoted this vertical dashed line here. This is a factorization scale at which we separate the two physics processes. Yeah? And this factorization scale is something arbitrary. Yeah? We are not. There is no physics law that tells us at what scale that should happen. Yeah? It should just happen somewhere between the proton, the scale of the proton, like a GeV, and the scale where our hard scattering is happening. But otherwise, it's arbitrary. And the fact that this is an arbitrary separation scale, this also allows you to derive later on evolution equations that will allow us to make statements about the parton dynamics inside a proton. This is something we will also talk about today and tomorrow. Huh? But this is the rough picture. So basically, the fact that when you work, when you look at QCD processes, at hadron colliders, with quark and gluon degrees in initial state, you're sensitive to non-perturbative physics, and you somehow have to treat them, and we do this by factorizing them off into non-perturbative objects that describe long-distance physics.
Just trying to understand. What you're calling factorization is the idea that you can kind of separate the non-perturbative physics of these parton distribution functions into something which you can study, and then the intermediate part where you will do the cross sections for these parton distribution. I mean the partons to some x. Is that the idea, that you can separate these three?
Basically yes. The idea is that we, when we want to compute a cross section for, say, LHC processes, we want to apply perturbative QCD. We have to work with quark and gluon degrees of freedom in initial state. Period. This is what we have to do, and this is what we can do for that center part here. We have quarks and gluons coming in, and they scatter and provide us with some final state. And this we can do in perturbation theory: leading order, next to leading order, next to leading order, and cubed leading order, and so on and so forth. Whatever we can achieve. Yeah? So this is basically the what we can do there, and the order of perturbation. I is basically, could be a quark or a gluon. So I here is just the parton.
Yeah. So
the incoming parton, and this can be a quark, an anti-quark, or a gluon. So basically, I runs over up, anti-up, down, anti-down, strange, anti-strange, and gluon. So in total,
right.
13.
For each I, that function depends only on mu, the scale.
For each I and j, you calculate.
If I of mu square, you said.
Okay, so
there.
Fi of mu squared, this is the thing here. So this is what comes in left and right. If we take the picture apart, and so here we have a proton, and then we are asking ourselves basically, in the longitudinal momentum approximation, this is what we are using here. Typically, what fraction of the incoming proton momentum can we assign to a specific parton, say an up quark or a gluon or a down quark. And this is just a momentum fraction. So we basically say the proton here has at 13 TeV, it comes with in the center of mass frame 6.2 TeV, and then we can distribute this momentum over all of its constituents. Yeah.
Yeah.
And
At very high energy, there is kind of a linearity being assumed here. That I understand at very high energy, but at low energy, where the factorization takes place, mu square, is it still supposed to work?
oh, sure. I mean, it is supposed to work from any scale above hadronic scales. Say, take a GeV, take a 2 GeV, up to 100 GeV. So basically, this is an arbitrary choice in the end that we can make, and the fact that we have a degree of freedom in choosing this factorization scale, this again gives us then some evolution equations with respect to the parton dynamics and also with the dependence of the hard scattering cross section here on this factorization scale. So this is something we can exploit. So if you were to if we go back to this picture here, and we think about the left hand side. So the left hand side is the physical cross section. It doesn't know about our concept of factorization, so it should be independent of this factorization scale. And then, if we were able to calculate to all orders in perturbation theory, also the right hand side should not depend any dependence on this, should not exhibit any dependence on this factorization scale. However, when we calculate to finite orders in perturbation theory, we truncate at a certain order of alpha s, and then a way to estimate the accuracy of these perturbative predictions is by simply varying this scale. And then we see if we truncate just at leading order, then we typically at a hadron collider we have a very large scale dependence. So then, depending on what kind of choice we make for this, we get largely different results. They can vary up between, say, 50 and 100%, and this is not a good approximation. So this is also what is forcing us to go to higher orders in perturbation theory, because then, as a rule of thumb, basically, once we do computations at next to leading order for the Large Hadron Collider, then this theoretical uncertainty that we estimate by varying the scale choice, that goes down to, say, 10 to 30%, but experimentalists are measuring to better accuracy than 10%, and this forces us to go then to next to leading order for key processes that are being measured, because experimental data is so precise and we want to reduce the theoretical uncertainty. And so then this can be achieved by going to next to leading order, or in some cases even beyond this, when you have very precise measurements with only a few percent uncertainty. So this is roughly the way forward, and I would like to walk you through those steps. Right. So this is basically what we'll be starting with in QCD.
Apart from that, there are probabilities, so we can multiply. I mean, is there any physical motivation?
You mean a physics motivation?
Physics motivation.
I would say it's simply it is separating different scales which are associated with different physical regimes. And so here, if you want to buy this argument, we simply separate short and long distance physics, and we do it basically with this master formula here. In different circumstances, like in particular, if you go back to deep inelastic scattering, where this has been, I think the formalism has been developed for the in the late 60s, early 70s for the first time. You can formalize it further by starting from time-ordered products of electromagnetic currents, and then you make a short distance expansion on the light cone, where you separate short distance parts on a light cone, and you remain with hadronic matrix elements.
So
They
there
are
was a
of
background,
certain operators.
okay, so previously people studied it on light cone and they could separate these things.
This is an alternative approach. This is then more if you follow the line of reasoning of operator product expansion, where you have a product of two electromagnetic currents and you simply expand them over all possible states in the light cone. But also there, you need to put in some large momentum, which you then use, and you need to put your physics on the light cone, which basically disregards transverse degrees of freedom. So it's the same thing here. So this convolution, this is the convolution in the longitudinal degrees of freedom of the protons. Yeah? So we disregard any transverse momentum dependence here for the moment. You can also extend it to include transverse momentum degrees of freedom, but then it becomes more involved as conceptually involved. Yeah?
Okay, thank you.
Yeah. Okay, good. So this is basically the setup, and this is what I would like to walk you through in one example. And the easiest thing to explain this
excuse me, I had one question. So here, yes.
Hi.
So hi. So in that slide you showed the factorization expression. There the factorization scale mu is it also the same as the renormalization scale? I mean, or can they typically be different? And if so,
Right.
what
So
are the
if
choices?
if we look into this expression here, I've just denoted there one scale mu, and in this case it's supposed to denote a factorization scale. Once we do our quantum corrections, there will of course be ultraviolet divergences. We will have to do renormalization, and then there will also be a renormalization scale. So once you go to the fine details, and you want to calculate this hard scattering cross-section here at high orders, then it'll depend basically on two scales. One is the renormalization scale, which you have to choose when you do your ultraviolet renormalization, and the other scale is the factorization scale, the thing where you separate
Low scale from the
the remaining collinear singularities that you will see and that you have to mass factorize. So there will be two scales, and both scales can be varied independently, yeah, because a priori they come from different physics. Typically what we do in the end, we fix both scales to some central hard scale which describes the central kinematics of a process, and then we vary them jointly or independently about a central scale. Yeah?
Okay.
Okay?
But they can be different.
They can be different, definitely. And this is also, especially if you go to higher orders, then you will just want to see stability in all directions, so you vary them independently. Yeah?
Okay, thank you.
So when you take the parton distribution function picture, they assume that all partons are non-interacting. But if you have high multiplicity events, or you go to saturations, will this picture also work?
Right. So if you have so basically this factorization picture here that we are drawing, this is based on the idea that we can pull out one parton out of the proton at a given time, and that we disregard any further interactions of the partons inside the proton. So there are kinematic regimes where people believe that some nonlinear dynamics of partons inside the proton become important, and there are an approximation, or that there are generalizations or further extensions of this linear evolution picture. In those kinematic regimes, how should I say, probing that regime is of interest to experimentalists and also to theorists. I would say it's a fair statement that we haven't seen compelling evidence yet, say of something like gluon saturation, simply because this happens in regimes where you have competing dynamics, so that the physical effects that you're seeing you can either attribute to, say, gluon saturation or to, say, low scale higher order perturbation theory effects, because this is happening also at low scales. But there are activities in colliders also to probe this further.
Hello. Yeah. Is it safe to comment that as long as mu f and mu both are higher than the proton mass itself, then this factorization formula is valid?
Yeah.
And if you bring down the mu f close to proton mass, then probably you need a finite mass correction in some effective field theory formulation.
Yeah, absolutely. So right, if you have data which is, for instance, deep elastic scattering data, which is taken at q-square values close to the proton mass, so at a few GeV, then you have to worry about higher corrections beyond that simple picture. So we have not some. This is the simplest QCD factorization picture, which holds for, say, high PT processes at the LHC. So think of this as you have QQ bar annihilation and you produce two jets back to back at high transverse momentum. Then this is where you can apply it, or think of this as the Drell-Yan process, basically. Yeah, you have QQ bar annihilation, you produce a Z boson here as a final state, and then this applies. So Drell-Yan process, actually, if we move on, I will discuss with you in more detail, and then you have some concrete example which you can associate to that picture. Okay? Right. Right. Yeah. Okay, good. Then let's start off. So the simplest example is deep elastic scattering. And there this factorization formula simplifies further, because at the core of deep elastic scattering is basically a photon exchange. So DIS process is basically of an electron. This is scattering of a proton. And then basically the proton is being X-rayed, if you wish, because there is a photon exchange between the electron and the proton. And then the proton, the photon is resolving the proton at a certain wavelength. Yeah, and if this is if this photon has low momentum, that means it will have long wavelength. It will resolve the proton at a larger scale, so maybe it'll see a few quarks. And if you increase the photon momentum, you go to smaller scales, you go to higher resolution, so you will be seeing more quarks and more gluons inside the proton. So this is roughly the physics picture that we have here. We are X-raying the proton, and we are putting this in the factorization formula here. And we say, okay, there is a hard scattering process. There is this incoming photon here, and it scatters off a quark here somewhere. And this is the part which we want to calculate in perturbation theory. And then there is this function f for the parton distribution, and this is telling us basically how we find a quark or a gluon with a given momentum fraction inside this proton here. So the physical cross-section is basically scattering of a virtual photon of a proton, and then we are fully inclusive on our final state, so we don't specify, we measure 4 pi, and then this is the factorization formula here. And the relevant kinematic variables are basically the photon momentum. So this is a space-like photon. This means capital Q squared is positive, and small q is the photon momentum. So being space-like, we have to take a negative sign here. And then the other variable which tells us about the proton dynamics in the proton is the Bjorken X variable. This is defined as q squared over 2 times the momentum of the proton dotted into the photon momentum. So this is a very scaling variable running between 0 and 1, and it basically tells us about what fraction of the incident proton momentum can we associate to any of the quarks and gluons in here. And now we would like to basically write this formula out and work it through in orders of perturbation theory. And measurements for this process have been done in the past at the Hera Collider. This is area of Hamburg. So this is the DESY campus. This is an old picture here because so the Hera Collider has now been mothballed. Has been switched off. All magnets are still in the tunnel. But the pre-accelerator Petra has now been turned into a synchrotron source. And yeah, this is the DESY campus here. Somewhere there is Hamburg Airport. And there is the football stadium here. And this is our office area here. So this is where I come from. But there will also be these experiments will also be conducted in the future. So currently there is at Brookhaven National Laboratory in the US. There is a refurbishment of the RIG Collider underway. So the RIG Collider will be switched off at the end of the year, and then it will be dismantled, and there will be a new electron ring put into place, so that then in the future we'll be having electron and ion scattering at high energies, and this will be basically doing deep elastic scattering collisions in the perturbative regime, because electron-proton scattering will be happening up to center of mass energies of 140 GeV. So basically there will be new data, also experimental data, coming from this collider in a few years. Alright, so on the theory side, if we go more into detail on how do we calculate the cross sections here. So we have an electron and proton scattering exchange of a virtual photon. Experimentally, you can measure the photon virtuality by measuring the angle of the scattered electron and its energy. So this is something that can be done. Then by that you can also measure the Bjorken X variable, and then in terms of the solid angle and the outgoing electron energy differential, you can parameterize the cross section in terms of prefactor, which you can derive from QED from Moch scattering of an electron on a point-like particle, and then because of the proton being a composite object, the cross section is then multiplied by 2 structure functions, which basically parameterize the composite nature of the proton, and the relevant structure functions are the structure function F1 and F2. You can also, depending on basically on how what polarization you associate to the photon, yeah. And those structure functions depend on the relevant kinematical variables x, Bjorken X, and q squared, which are the ones that we need in order to make statements about a proton structure. And then in deep elastic scattering, if we go to the Bjorken limit, taking q squared to infinity and keeping x fixed, then the parton model in first approximation tells us that those structure functions are simply a product, a sum of a charge-weighted product of all the parton distributions that we have in the proton. So basically, we sum over up-down strange gluon distribution in the proton, and we multiply it with the quark charges squared, and sum it all up. Yeah? So this is what we have at leading order, without any further QCD corrections. And now QCD corrections basically tell us also about the scale dependence of the structure function, because if we implement our factorization picture, then this convolution this convolution equation that I had before. This we can write down now in full glory with all variables specified. This is now here as for the structure function f2. This is an integral over a scaling variable psi of some hard scattering coefficient function. They are also sometimes called Wilson coefficients, and those Wilson coefficients are taken at variable x over psi. They depend on alpha s, at which order of perturbation theory we work, and then they're being multiplied with the Poisson distribution evaluated at psi. So this is the way we implement this convolution here. Poisson distributions evaluated at psi, and coefficient functions evaluated at x over psi, and then everything integrated from x to 1. So this for this specific process here for deep inelastic scattering, how this convolution is really written out in terms of kinematical variables. And then the coefficient functions are the quantities of interest, and those we want to calculate in perturbation theory, and they are known for leading order, next to leading order, and next to leading order, so they are known up to here. This is currently work in progress, so we can push the perturbative series pretty far, and today in the following slides I just would like to tell you how to compute those quantities here. Right, and the leading order coefficient function here, this is really very simple, because in order to compute this, you just need to look at the scattering of a virtual photon of a quark. So this is a 2-to-1 process, and a 2-to-1 process is kinematically constrained. And in terms of those scaling variables that we use, scaling variable Moch and x, the result for the squared matrix element, which goes into the Platonic structure function, is just the charge of the quark squared times a Dirac delta function in 1 minus x. Meaning that the Moch and x variable has to be constrained to 1 in order for this bond level process to happen. Huh? So then we are done. And it basically, if you take this for this coefficient function, you stick it back in here, so you basically replace this by a delta function in x over psi. You will see that the convolution here trivializes, and you will get back the Poisson distribution at x, and this means you will be getting back the leading order Poisson model expression here. So basically computing this quantity here in QCD perturbation theory just gives you back the leading order expression for the Poisson model for the structure functions. Huh? With only x dependence and no q square dependence. Now, the q square dependence is something that has been discovered early on, and that led people to believe that QCD is the right theory of the strong interactions, because in the early 70s, in the DIS measurements at SLAC, people measured those structure functions and they found some q square dependence in the data, and then they started to think about the higher order QCD corrections. And now if we want to compute them at the first order, then we have to consider, like we did yesterday, for the case of E plus E minus annihilation, we have to consider two classes of diagrams. We have to consider the virtual corrections to our bond process, and then we have to consider the real emission of one additional gluon. Now the virtual corrections are simple, because it's the same diagram that we have considered already yesterday. It's just now different kinematics. So yesterday we have considered a photon going into QQ bar pair, and there was a gluon exchange, and now we consider the photon and a quark scattering, and they have a virtual gluon exchange here. Huh? So it's this loop diagram here. It's the same expression as yesterday. The kinematics is again constrained because it's Born kinematics. So we have the quark charges squared color factor CF in QCD alpha s over 4 pi, Dirac delta function, and we have in dimensional regularization, we have poles in epsilon. So the double poles here come from this gluon being soft and collinear. This is a collinear singularity, and then there are some finite parts. And the only difference in its expression with respect to what I told you yesterday is now that the hard scale q squared here is basically the space-like momentum squared, negative space-like momentum squared of that photon here. And in E plus E minus collision yesterday, it was the center of mass energy, so it was a time-like quantity. No? So that's the only difference that we see here, but otherwise the expression is the same. Now, we notice, and we also know that this is not a complete answer, because in order to get something infrared finite, we have to take into account the real emission contributions and cancel those singularities. Now, the real emission diagrams that we have for this process are also not complicated. This is then 2-to-2 diagrams. In one case, we can emit a gluon from the incoming quark line, and in the other case, we emit a gluon from the outgoing quark line. And just two diagrams. We add them up, we square them, and then we have to integrate over the phase space of the outgoing quark and the outgoing gluon. And we keep a differential in the parton momentum fraction x, meaning we have a one-dimensional. We have a function in the end that depends on just the Bjorken x variable in the end. And if we do the entire phase space integration and we add what we have for the real emission diagrams here, we add it with what we have for the virtual corrections here, then this is the final answer that we get. So it's a function depending on the parton momentum fraction x. So basically on the fraction that we on the variable x variable defined as q squared over the parton momentum times the photon momentum. And what we see here, that adding the real and the virtual corrections, we see that the double poles that we have here, they cancel. But then there are single poles in epsilon remaining with a function, with a specific function depending on x. And then there is some finite remainder. And now if you take a sharp look at this function, this 1 over epsilon pole here multiplying this polynomial in x, this is again the QQ splitting function at leading order and QCD that we have already discussed yesterday when we were looking at the way how we can understand gluon emission in jet processes. So it is again the divergent remnant which we have here is now a collinear singularity, and it describes the collinear emission of a gluon here from the incoming quark line. And this is basically telling us, if you wish, the transition of a quark going into a quark under the emission of a gluon. This is how you can read it. Given that the incoming quark has a certain momentum, and then the outgoing quark here has a certain momentum fraction of the incoming quark in this collinear approximation here. So it is basically giving us the collinear singularity associated to this incoming, to the gluon radiation of the incoming leg, and this is something that we cannot cancel by any other Feynman diagrams that we have, because to that given order we have already put in all the Feynman diagrams, and this is a manifestation of what I said initially, that for scattering cross sections with initial state hadrons, we cannot, purely from perturbative QCD, cannot get infrared finite results, but we have to work more. We have to apply this concept of mass factorization. Yeah? And the way this is then
yeah, in this, like, is there a way to see from where the zeta function is originating from in the middle, the coefficient of delta? Yeah.
This one here.
Yeah.
Okay. So this is then the next thing is the coefficient function. So I'll discuss in a minute. And it depends again on functions of x, and it has here a Riemann zeta of 2, which is pi squared over 6. And this pi squared over 6, so there is some pi squared over 6 coming here from the form factor, but there is also some pi squared over 6 coming from the real emission diagrams if you simply do your phase-space integration. Okay, right. So we want to get rid of this additional collinear singularity, and the way out is to first of all I take the lengthy expression on the previous slide. I basically abbreviate. So this is the splitting function. This I call the coefficient function. So I write it out in shorter notation. I call this now a bare Platonic structure function at order alpha s. I have the collinear divergence multiplying the QQ leading order QQ splitting function. I have my coefficient function, and then in dimensional organization I have higher order terms in epsilon, which I can drop here. And then the way out is basically to go back to my initial factorization picture here, where I have the convolution of a coefficient function with a pattern distribution function, or even go back further a little bit here, and say, okay, initially I started this computation not specifying what kind of pattern distributions I use, and I consider them as being bare pattern distributions, and I would like to consider them now as renormalized pattern distributions, so that I also renormalize them, meaning that I absorb all collinear divergences in suitably redefined pattern distribution functions. That means in my factorization formula, I replace the bare pattern distributions I started with renormalized ones, and those renormalized ones are just the bare ones where I have subtracted the collinear singularities. Then I put everything together. I can then expand again at a given order in alpha s, say to order alpha s squared. And then those collinear singularities cancel. I remain only with a finite coefficient function, and the remnant of cancelling this collinear singularities is basically a logarithm multiplying the leading order splitting function, because my original calculation of the bare Platonic structure function had a ratio of mu squared over q squared. My pattern distributions live at the scale of the factorization function, so they come from dimensional considerations. They come with a mu squared over mu f squared, where mu f is the factorization scale, and the difference between those two scales then gives me a logarithm of q squared over the factorization scale times the splitting function. So the price of doing this collinear factorization is that I get a finite on the plus side as a benefit. I get a finite cross section, and on the minus side, the price I have to pay is at fixed order and perturbation theory. I'm retaining some logarithms of the factorization scale, and then those logs, they are responsible for residual scale dependence in my physical structure function. So this is then to order alpha s. This is then the full expression for the correction. I have explicit scale dependence here. I see explicit dependence on the scale q squared here, and I have some finite corrections in the coefficient functions which I have to take care of. How I define my factorization scale? Well, this can be, you can consider this as one definition of a factorization scale. Yeah, I mean, this is in that simple example. If we do it on the side of perturbation theory in this way, and we say we want to absorb the collinear singularities and redefine pattern distribution functions, then this can be considered as the definition of the factorization scale. Yeah? If you come from the OPE picture, then it's basically the scale at which you separate Wilson coefficients and operator matrix elements, but here consider it as a definition.
So in renormalization, so there are some renormalization conditions, and from those conditions we get to know like what are the pole structure and what are the finite terms. So the same, if I see like in the same way, what will be the renormalization conditions here?
I don't quite understand.
Like for QD, when we do the renormalization, so
Yeah.
we measure the charge and we do
Okay.
put the renormalization condition there.
Yeah, but here we haven't done any renormalization because you see we are working. So this just depends on alpha electromagnetic at leading order, and then this is the first time we have dependence on alpha S, and so all the singularities here, they are all infrared. There is no ultraviolet singularity in this loop diagram, so we don't have to renormalize here. There is no alpha S or other renormalization that we need to do here. It's all massless quarks and gluons, yeah. And then this is all real emission diagram. Also there we don't have to do any renormalization. So only if we go to second order, to NNLO, then there will be for the first time ultraviolet divergences in the diagram, and then we also have to do the loop integration. So that also tells you, since we didn't have to renormalize the alpha S that I put here, we didn't specify the scale yet of alpha S that we put here. So this is the first order correction of the strong interactions, and we were not forced to renormalize yet, so we didn't really specify the scale of alpha S yet. So in order to do that, and also to get full interplay between renormalization and factorization scales, then you have to go to the next leading order.
So my question is a bit different. Like when you write this pair, renormalized pattern distribution as a pair and some counter term. So how do you find this counter term? So what are the conditions actually you impose here to find the counter terms?
Well, basically the condition for that counter term is that I have I can think of these bare pattern distribution functions as I can think of them as being operators describing the quark content in a quark. So I can think of them as being a quark operator, and then I can do loop corrections to those objects, asking for the probability of finding a quark inside a quark at order alpha S, which means I have to have some gluon radiation. And in this way I can also give an operator definition for those quantities. I can do loop corrections. I will see that the anomalous dimensions of those composite operators that I define to describe the quark content in a quark precisely have an anomalous dimension, which is precisely given by the Mellin moments of this leading order splitting function. So this is a different way of seeing it. Yeah. So this would be coming more from the operator product expansion, where you can basically calculate these quantities as anomalous dimensions of certain local composite operators. So this is a different way. But here I would say I would simply take this as a definition, and then you can continue and it works. This is what I would argue here. And I mean, for the sake of the lecture, I would say take this as a definition here. We take this as a renormalization condition for the quark PDFs, and we take it and then we apply it also to another perturbative process, namely Drell-Yan, and we see whether we get a sensible result for Drell-Yan consistent or not. Okay? So this would be the test that I can offer you here. Okay?
Thank you.
defined, which was the product of Fi's and the sigma, that remains the same. It is just that you are transferring some contribution to Fi's and removing the
Right.
singularity from the sigmas.
Absolutely, yeah.
Yeah, that is what is being done.
Exactly.
So initially, what we pretend to calculate as sigma was actually wrong because it had the divergence. So we are transferring it to.
Exactly.
So now, so when at higher loops, when you have both the two types of divergences, including the UVN, is there a proof that this procedure will go through to all orders?
So there are factorization proofs to all orders for deep inelastic scattering. I would also say for Drell-Yan, people are debating this a little bit. So there are people who are a bit, I would say, they are a bit more picky on details of how you basically when you want to prove this factorization, this factorization to all orders, then it's a question how can you to all orders prove that you separate gluons, gluon exchange at all length scales, maintaining gauge invariance. So this becomes a bit involved, but these proofs exist. So for DIS, I think they are undisputed. For Drell-Yan, people are still taking active interest in this. From a practitioner's point of view, I think we simply calculate to a given order of perturbation theory, and it always works. So this is my approach to it. So from the practitioner's side, it has never failed us.
One more question.
Yeah.
When you have both the UV with same thing with the UV divergence, you will have another mu coming from the
Right.
UV divergence. Will you take two epsilons or is the same epsilon?
No, we basically, I mean, the nice thing about dimensional organization is that we can always use
One.
So we basically shift epsilon always by d always by 4 minus 2 epsilon, and then this regulates both infrared and ultraviolet. The price we have to pay, we cannot distinguish if we just look at the expression, but once we apply the UV renormalization, then we can extract those, and the rest will be IR. And since we know that both ultraviolet and IR divergences have a certain universal structure, then this is also predictive.
Yeah, that works, but in principle, if we had used epsilon and epsilon 2, would it still work?
If we had
To make sure that we are not mixing the divergences.
I think, I mean, in practical,
Like it's a analytic continuation would have been done independently.
in practical terms, I think it can be done, but it becomes very tedious. So I'm not aware that, say, beyond simple examples of DIMREC, this has been exploited more thoroughly.
Okay.
Yeah. Okay. Good. So what I wanted to point out is also that now that we have a finite physical cross section or physical structure function, there is this coefficient function here, which is the giving parametrizing the hard part. So it is this expression here. So this line and this line. And the interesting thing here to denote is it has this plus distributions, the log of 1 minus x over x and 1 over 1 minus x plus distributions here. So they are integrable quantities, but they are large when you approach the limit x to 1. And you can classify them by going to Mellon space, so you can make a Mellon transform of this. And then this logarithms 1 minus x over 1 minus x, they give you a double logarithm of the Mellon moment n when you take n to be large. The single distributions give you log of n when n is becoming large. And so you can do some power counting here at each order in perturbation theory. So to the order alpha s to the power n in perturbation theory nth order, you find plus distributions with a log 2 n minus 1 of 1 minus x over 1 minus x, and they translate into Mellon space logarithms alpha s to the power n log to the power 2n of the Mellon variable n. And those are large Sudakov logarithms, and they appear systematically as a remnant of cancelling this collinear singularity here. Yeah? So once this collinear singularity is cancelled, the remnant are these double logarithms in n space, or large plus distributions in x space if you wish. And knowing the underlying structure of factorization, you can then set up some renormalization group equation that resums systematically all these large logarithms, say in n space, and exponentiates them. So that means for the coefficient functions in n space, you can then write down basically some finite prefactor, and then you can resum all these large logarithms in some exponential, where you have some function which then resums those quantities to leading, next to leading, next to next to leading log accuracy, whatever you have achieved. So I think we've pushed this to the highest available limit with Gautam Das some time ago. And this then is another example of how you can then implement or realize resummation of large corrections from collinear emission. So yesterday we had discussed in the lecture, and also in the tutorials, we had discussed a way how we can phrase the same physics as a Sudakov form factor that you can put into a Monte Carlo for pattern. And here we basically can capture the same physics in an analytic expression, which is resumming specifically these large logarithms in n space then. And this is some numerical results just showing convergence as you go to higher orders in logarithmic accuracy. But let me skip this in view of time. And let's just look at the Drell-Yan process briefly. So this is the other basic QCD process. And this now really applies to, say, LHC. Well, we have two incoming protons, QQ bar annihilation, and we have a boson. And this decays, say, Z boson decays into U plus minus, or E plus E minus, this can be measured. And at an inclusive level, this process can be described by also two scaling variables, two kinematic variables. Now we have the center of mass energy S, and we can call it again capital Q squared. This is now time-like. Previously we had some space-like quantity, and we can also define a scaling variable X, very similar to the Bjorken X we had before. And the scaling variable is just the mass of this gauge boson here squared, so it could be W or a Z boson, mass squared divided by the center of mass energy. And because of energy momentum conservation, you can then immediately see that also the scaling variable can only range between 0 and 1, because phase space is constrained. Right. And this process has been measured. This is a plot of early measurements of W and Z boson production cross-section. So this is the SPSS measurements that had been made at CERN that led to the discovery of the W boson in the 1980s. This is then tevatron measurements, and by now we have at a scale of 7, 8, 13 TeV. We have much more data from the LHC, so this is really very, very well understood process. And if we're interested now in the QCD corrections to this process, and we would like to understand how to compute those quantities, then writing out this factorization formula that I had on the initial slides for this process, this is what we have to consider. So we have the process proton-proton collisions producing us a vector boson. We have two parton distributions, one for the incident proton 1 and one for the incident proton 2. Out of the first proton we pull a parton I, out of the second one we put a parton J. We sum over all the combinations that exist there, and we multiply this with our hard partonic scattering cross-section for parton I and J, producing us a vector boson. So the variables that are used here is tau, which is the center, which is the mass of the gauge boson divided by the center of mass energy, and then in the convolution integrals I have integration variables x1 and x2. So they are just the momentum fractions of the incoming partons with respect to the original proton momenta. And the convolution integrals go, the outer one, dx1 over x1 is integrated from tau 1 to 1, from tau to 1. The x2 over dx2 over x2 is integrated from x1 to 1, so this is nested integration. And then the first parton distribution is evaluated at x1 over x2, the second one is evaluated at x2, and then in this way the hard partonic cross-section is to be evaluated at tau over x1. So in this way we have expressed the double convolution in terms of a double integral over the scaling variables x1 and x2. And the quantity here is what I want to calculate, leading order and next to leading order cross-section. So the kinematics, if you go to differential kinematics, then you basically parameterize this in terms of transverse mass and cosine of the rapidity. We always integrate out the azimuthal angle that we have here, and the relevant quantities at the Hadron Collider to measure are basically rapidity or pseudo-rapidity if you neglect the proton masses and the pseudo-rapidity and the transverse momentum. And integrating over the transverse momentum, we typically end up in terms of the pseudo-rapidity. Now the Born cross-section is, we can calculate it quickly, or we can even, by physical arguments, we can basically derive it from what we have learned yesterday, because yesterday we looked at E plus E minus annihilation going to QQ bar, and now we are basically looking at the reverse process. We are looking at QQ bar going to E plus E minus annihilation. So we have the same cross-section as we had yesterday, only difference is now we have our QQ bar pair in the initial state, so they come with 3 colors, and we have to average over the quantum numbers in the initial state, and compared to the E plus E minus annihilation cross-section that we considered yesterday, the only difference is we have to put a 1 over NC, NC being the number of colors, one additional factor we have to put there on top of the cross-section that we had yesterday. Yeah? And then typically what is being measured is the invariant mass of the invariant mass distribution of the gauge boson. We can write the cross-section as a differential with respect to the invariant mass of the gauge boson, and at Born level this is constrained, so the center of mass energy has to match the gauge boson mass, so we just get a delta function. That means if we stick in a delta function constraint here into our formula here, then the leading order cross-section simplifies, and we just get the product of the quark and the anti-quark parton distributions at the different momentum fractions x1 and x2, and from the delta function here, from the center of mass energy constraint, we get a delta function relating to the 2x variables. That means we only have to do a one-dimensional integral here, convoluting the incoming parton distributions x1 and x2. So this is the Born cross-section, and this is how a measurement of the invariant mass distribution looks like. So we typically we can basically measure the whole range of invariant mass distributions, but we are mainly interested here, if we have lepton anti-lepton pair in the final state, we are of course then interested in the cross-section around the Z boson peak here, because this is giving us the dominant part of the data. If you are measuring this also differential in rapidity, this is just a side comment, then you are basically binning in rapidity in terms of these x variables here is the ratio of x1 over x2. So if you're also binning in terms of rapidity, then you're getting a local measurement in terms of the Poisson distributions. And this is why typically at the LHC now we are using also rapidity distributions for the Drell-Yan process in order to extract information about the proton structure. Right. But just to wrap up with the QCD corrections, so that the leading order part in terms of the scaling variable x, which is just which is entering here in our formula. So this tau over x1 I abbreviate as x just for simplicity. Leading order cross section is just giving us a delta 1 minus x here, omitting prefactors like alpha, QED and so on. And then the higher order corrections, virtual corrections here, is giving us again this loop integral here. This has infrared and this has infrared singularities. Now I've put explicitly the scale here of the gauge boson mass. It's constrained, kinematically constrained with a delta 1 minus x. And the real emission contributions is a gluon emission from either of the quark lines, like from here and from here. So we have a diagram where we emit from the quark line, we have another diagram where we emit from the anti-quark line. We add these two diagrams, we square them, and we integrate over the phase space up to differential in x. And then we again find that the infrared singularities cancel, and we are left with a collinear singularity, which is multiplying the splitting function. And now the only difference is here that the collinear singularity that we are finding is now 2 times the splitting function, because we have gluon emission from the incoming quark or the incoming anti-quark. In DIS case, we only had one incoming quark, so the collinear singularity we found was just 1 times the leading order splitting function. Now we find the collinear singularity proportional to 2 times the leading order splitting function, plus some finite bits and pieces. And then we follow the same procedure that we devised for the mass factorization in the DAS case. So we take our bare quark distribution, we subtract the same counter term here to get a renormalized Poisson distribution. But now in the Drell-Yan case, we also have we have 2 Poisson distributions parameterizing the 2 incoming partons, and so so having a quark and an anti-quark, which are both get a subtraction of this counter term here, we are then able to cancel precisely this double singularity here in 2 times the leading order splitting function, because one splitting function is cancelled by the quark, incoming quark, redefined incoming quark distribution, and the other splitting function singularity is cancelled by the redefined incoming anti-quark PDF. So in that sense, things work out nicely, and we finally get a finite physical cross-section at the factorization scale μf, and now we have a scale-dependent log proportional to the log of the gauge boson mass over the factorization scale, multiplying then 2 times the leading order splitting function and some finite quantity. And this is then the finite physical prediction for the Drell-Yan cross-section at next to leading order. Right, so this is what I wanted to say, and then we look at we take a brief look at the finite quantities here. So once we've absorbed the collinear singularities, then this part here is then the finite correction that I've abbreviated here. And again, this has large plus distributions as a function of x, and again we can perform threshold transformation, put it to Mellin space and then resum it in Mellin space or directly resum it in X space. And if you have any questions on this, then there are expert people in the audience here, so all questions on that part can be addressed to Ravindran. And that brings me to the summary of what I wanted to tell you today, providing two examples of how we can understand factorization for inclusive DIS or for the Dralian process, and I've shown you how to calculate the next to leading order QCD corrections for the two processes, and I've tried to illustrate how we can apply the factorization procedure and get a finite prediction that we can apply to experimental data comparisons. Thanks a lot. So while you're thinking of questions, let me also say there is another tutorial. So there is, I hope also not difficult one, where you're supposed to look at the Dralian process, and then you can write down this factorization, general factorization formula. You can take some toy ansatz for this PDFs, and then I've given you here the partonic cross-section at leading order, and you can do the kinematics considerations. You can see how this factorizes, the full cross-section factorizes in terms of the cross-section of QQ bar annihilation, in terms of a Z boson, and then a Z boson decaying into a lepton pair. So basically all formula are given there, and you can just go through that.